Hello, welcome back. New topic, important topic, implicit differentiation, using the chain rule for good. So I love this topic. I feel like if this makes sense, then so many other things make sense, and your ability to write complicated formulas and not simplify them, and then still be able to find the derivative using implicit differentiation is so empowering. It feels so good to me. Okay, so here's the setup that the way I'm going to try to introduce this. What if I don't have a function? What if I just have an equation? Something like x squared plus y squared equals 169. So that would be, I hope you know, a circle, and a circle where the radius is the square root of 169, also known as 13. We could even get weirder. We could look at this x cubed plus y cubed equals 6xy and get some crazy curve like this. It can get so much weirder. These are still pretty simple equations, but plotting solutions to things when there's x and y's on the same side of the equation and we can't always even solve for it, you can get lots of neat shapes that maybe you hadn't even considered. In particular, we can't solve for y directly because these aren't functions. So for any given x value, you've got multiple y values. In some nice cases, you could write it out, like for the circle, you could write it out using a plus or minus square root, and that would give you the two different answers, but there's no reason why we couldn't have many, many, many answers, or even infinitely many answers using something like this. So we wouldn't expect to be able to solve for y and get a formula that has those answers. So could we still talk about the derivative? It makes sense that we'd still have a tangent line at a point. There's still a notion of rate of change happening. It's just going to depend on both an x and a y value, because the tangent line here versus the tangent line at the bottom are going to be different even though they have the same x value. I'm going to need to give you a point on that curve. Okay, let's back up. Let's try to make some sense of this. How do we do it? So let's just say I want to take the derivative of y, d dx of y. There's a lot of ways of writing this, but I'm going to stick with Leibniz notation here for a second, and I'm going to say this is dy dx. Oftentimes, even with implicit differentiation, you will see people write y prime. That's fine. I'm going to really encourage you to write it like this for this section, and also definitely for related rates. I think it makes what's going on a little bit more clear, especially in future sections. Okay, so we don't know what y is. It's just some function. And whatever it is, its derivative is dy dx. What implicit differentiation does is it says there's nothing special about y or x. Right? These aren't functions anymore. So they're just they're peers, x and y. We should be able to take the derivative of either one. It just so happens that if I take the derivative of x with respect to x, we would get dx, and then on bottom is dx. Maybe you can tell what this is. It's just a 1. So we still get the answer we think out, 1, but that's because the rate of change of x with respect to x is 1. If we wanted to, we could talk about dx dy. How does x change as y changes? So they're in this nice mutual relationship. We're not forced to think of one as subservient to the other in any way. They're just functions. Y is a function, or rather, I mean, they're not even that, right? They're just kind of a relationship. We can treat it kind of like a function and say, well, whatever that derivative is, it's dy dx. Whatever the derivative of x is, it's with respect to x, it's 1. So 3y squared, what would the derivative of that be? Treat it like anything else. We'd say leave the 3 out front. Let's do this in blue. Leave the 3 out front. Multiply by, bring the 2 down. Y, I'm not going to write to the 1 here, but it's to the 1. And then my chain rule says, well, I need to take the derivative of y. I need to multiply by whatever the derivative of y was. Well, that's just dy dx. Okay, so this is just my chain rule in action. The 3 hangs out. The derivative of a function squared is 2 times that function. The derivative of y, in this case, that inner thing, using the chain rule, is dy dx. Let's do it again over here, now with a product rule. The product rule says take the derivative of x, which is a 1, leave the y alone, plus leave the x alone, and multiply by the derivative of y. That's just dy dx. Okay, maybe confusing as to why we're doing it, but take a second and make sure that you can actually do those two things, because that's going to be the building block of what we do next. Okay, so how do we tackle something like x squared plus y squared equals 169? This is so smart. What do we do in algebra in general? Whatever my operation is, if I do it to both sides of an equation, if the left side is equal to the right side, I take the derivative of both sides, it should still be equal. Let's just take the derivative with respect to x of both sides. So it looks like I'm going to get a 2x. I can still go term by term. I'm going to bring that 2 down times y, but now I need to do the chain rule, and I'm going to get a dy dx. Notice I could have done the chain rule on this x squared. I would have gotten, right, 2x and then times dx dx, but dx dx is just 1. So if we really want to write a dx dx right here, go for it, just like we write a dy dx here. But that dx dx is just always going to turn out to be a 1. Okay, we didn't quite finish. We have to do the right side as well. The derivative of 169 with respect to any variable is just 0. Neat. So now I have now I have an equation with my dy dx in it. This is now an algebra problem. I want to go ahead and solve for dy dx. I want to know what that derivative is. So what I'm going to do is I'm going to bring everything that does not have a dy dx in it to the right side. So I'm going to get negative 2x equals 2y dy dx. Okay, and now I'm going to divide by that 2y, and I get dy dx is equal to negative 2x over 2y is just negative x over y. Amazing. So what I have now is this beautiful formula for my derivative that depends on both x and y. We could even plug in, right? So if I wanted to, I could say, all right, at 0, 13, my dy dx is equal to negative 0 over 13, which is just 0. What we need to actually plug in is both an x and a y. And that x and the y, hopefully, actually satisfy my original equation. I'm on this circle. Otherwise, what would happen is I'd be on maybe some other circle. And it turns out that's what you get in this case. Because the derivative of any constant is 0, this part defines the radius. And so if I pick a number that does not satisfy a point that doesn't satisfy this equation, really what I'm saying is on some other circle centered at the origin, what would the rate of change be? So in this case, at 0, 13, that is this nice top spot right here. Yeah, it makes sense that my rate of change is 0. Fantastic. Okay, let's go ahead and try my other function while we're here. It's pretty darn similar. That is on purpose. It's got an extra wrinkle to it. I'm going to look at x cubed plus y cubed equals 6xy. I'm going to take the derivative of the whole thing. Try it with me. Even try it before me. See if you can do it. 3x squared plus dx dx, or sorry, times dx dx, but that's just 1. Plus, I bring the y down, 3y squared. My chain rule says take the derivative of that inner function, which is a y. So that's dy dx. And now there's a bit more work to do on the right side. So I'm going to go ahead and write a 6. I'm going to do my chain rule inside of there. So it looks like I get a 1 times y plus, leave the x alone, x times the derivative of y is just dy dx. Great. So I've done the calculus part, right? I did it. I took the derivative just basically using rules I know. There was a product rule and a chain rule in this one, as well as a power rule. Now it's a matter of algebra. And sometimes for some students, it's actually the algebra in here that causes them trouble. So be honest with yourself. What is the part that is messing you up if you're having some struggle? Is it this first derivative, or is it really just solving for dy dx? So how do I solve for dy dx when there's a bunch of them around? I'm going to bring everything with the dy dx to the left side and everything without to the right side. So it looks like I get a 3y squared dy dx minus 6x dy dx. So that was me just grabbing everything with the dy dx in it, and everything without I'm going to bring over. So it looks like I have a 6y, and then I've got that 3x squared term. Okay, looks pretty good. Bring everything to one side. Why would I do that? Well, as long as everything on the left has a dy dx in it, nothing on the right does, I can factor out this dy dx. Pull it out from the left side. And believe it or not, you've probably done problems like this in an algebra class in the past. It just didn't have a derivative that you're solving for. I'm so close now, I just have to divide. Once I pull out that dy dx, there's just one more step. It looks like it is a 6y minus 3x squared divided by 3y squared minus 6x. That is my dy dx. And it's pretty much going to look like this every time. Bring everything with dy dx's to usually the left, everything without to the right, factor out the dy dx, and divide. And you're going to get something that may or may not look a little nasty, but it's fine, because if I need to plug in a number to there, or a point into there, I can. Notice that there are some points that don't work. In particular, if the denominator is 0, we still need to worry about that. Okay, but we need to give both an x and a y. And going back up here, you should expect some kind of weird things because, in particular, the function crosses itself. So there's this really good question of, hey, what happens at 0, 0? How do we actually deal with that? And almost as a good thing, you notice that if I plug in 0, 0, I get 0 on top and 0 on bottom. So the math is actually telling you something weird is happening here that you need to worry about. We actually like that. We like it when the math tells us something is weird rather than just giving us one answer and not telling us the other. All right, very cool, very cool. Let's go ahead and up the ante a little bit. When is the tangent line to that same function, that same, I guess, graph, horizontal? So we're asking ourselves, when does that whole thing equal 0? So this is a little bit of a side topic here, right? But it's worth pointing out that we can answer some of the same kinds of questions, sometimes with a little bit more work in this case. So to have a horizontal tangent line, we are asking ourselves, when is that derivative function, which gives us the slope? Well, if I want it to be horizontal, that has a really specific meaning. We're asking ourselves, when is it 0? Okay, so now we want to solve for this. I'm going to multiply both sides by that denominator, which I do still need to worry about when that denominator is 0. I don't want to multiply both sides by 0 here, but let's go ahead and do it. 6y minus 3x squared equals 0. When is the numerator 0? So that's a nice description, but we can actually do a little bit better if we want to, because we also have this equation. We have this nice original equation. And so we should be able to plug one into another. Let's go ahead and try this. We're just going to take a minute to do some algebra here. So if I solve this, I get y equals, looks like x squared 1/2 x squared. All right. Did that kind of in my head. Hopefully that wasn't too bad. That means I can take that, and because I still also need to be on that curve, I should be able to plug that into my original equation of x cubed plus y cubed equals 6xy. This is actually a system of equations that needs to both be true at the same time to have a horizontal tangent line. How do we solve a system of equations? Well, one of the standard ways is to plug in. So if they need to both be true at the same time, I should be able to write the same thing, but with that 1/2 x cubed plugged in. So I get x cubed plus 1/2 x squared cubed equals 6x times 1/2 x squared. So wherever there was an x, wherever there was a y, I plugged in 1/2 x squared. And this is the basic technique, right? That when you need to actually solve for something like this, you realize you have two equations around now at your disposal. We could keep working this. I'll go a little bit further here and say, let's bring everything to one side and simplify. So this is an x cubed. This is plus 1/2 x to the 6th. This is equal to 3 x cubed. When you have a polynomial like this, you always bring everything to one side. So it looks like I have a 1/2 x to the 6th minus 2x cubed equals 0. I can factor out an x cubed. I'm going a bit quick here. The algebra wasn't the real point of this example so much as the process. So I would get 1/2 x cubed minus 2 equals 0. Now that this is factored, I can solve them independently. So I would get at this one would give me x equals 0. This one gives me 1/2 x cubed minus 2 equals 0. I could try something fancy, but I'm just going to solve. So it looks like I get x cubed equals, I bring the 2 over to get a 2, and then I divide by 1/2, so I get 4. So I get x equals the cube root of 4. Boy, I hope I did all that right. So I would get these two different answers, and I should go back and check, does this make sense? It turns out that this x equals 0 is going to require a little bit more looking at. When I try to plug that back into my original equation, that x equals 0 is this weird spot right here. However, you do get these other two tangent lines where it is this other tangent line where it's horizontal up here. Okay, great. So that was a bit of work. The main point here was that it's worth saying, oh yes, I can still use my knowledge from before to say set the derivative equal to 0, but that I've got two different equations flying around, I might need to use them both. All right. Chances are that was a bit much to lead up with. I just wanted to warn you that was there. Let's take a step back and let's try to do a couple more direct ones before we get too confused. Okay, next time we will do a bit more practice.